Okay, so I am going to try to record a lecture to see how it goes on Chapter 3, which includes chemical reactions and reaction stoichiometry. So in class the other day, we talked a little bit about why stoichiometry is necessary. So in the end, it all comes down to the law of conservation of mass. So all this states more or less is that matter cannot be created or destroyed, which means that if I have some amount of a certain chemical, so say 10 grams of carbon on one side of my reaction, that 10 grams can't simply disappear. It has to be equally represented on the other side of the reaction, which we're going to talk about in a minute. Okay, so for those of us that are already familiar with the terms, that means if I have 10 grams of carbon in my reactants, I must have 10 grams of carbon in my products as well. It could be reorganized, right? It may have started as pure carbon or started as carbon dioxide and end up in some kind of totally different compound, but the total mass of the carbon has to be conserved. Okay, so in chemical equations, we have two main sides basically of the equation. So on the right side, or sorry, on the left side, we have the reactants, and on the right side, we have the products. This is for an irreversible reaction. So you can see the arrow right here is only going in one direction. So when the arrow only goes in one direction, so for example in this equation I have 2 moles of hydrogen, or H2 combining with 1 mole of oxygen, O2, to form 2 moles of water. This arrow is suggesting that this is a irreversible reaction. In reality though, most reactions are actually reversible. And if that is the case, then if I want to clarify about reactants and products, I have to say whether or not I'm discussing the forward or the reverse reactions. So for the forward reaction, this would be correct, that these are the reactants and these are the products. However, for the reverse reaction, it would be reversed, where the products for the forward reaction are now the reactants, and the reactants for the forward reaction are now the products. But we'll talk about that more later. Okay, so what is in a chemical equation? Chemical equations tell us a lot. They tell us what elements are involved. They tell us how much of each element I have. And then they tell me how many moles of each molecule I need in order for my equation to be balanced. So in this chemical reaction, I have again my reactants on the left side and my products on the right. Okay, some numbers that we need to focus on are these little subscript numbers, as well as these cofactors, which we're going to call our stoichiometric coefficients. The subscripts are going to tell us how many of each element are in a given molecule. So for example, this CH4 contains 4 molecules, 4 hydrogens linked to a single carbon, so 1 is implied when there's no number. Whereas the coefficient, for example, right here, the 2 after the oxygen tells me that there's 2 atoms of oxygen in every molecule, right? So this is because oxygen exists as I want to say divalent, but I know that's it's a diatomic, there we go. It's a diatomic molecule. The 2 in front, this stoichiometric coefficient of 2, is telling me that I need 2 moles of O2 in order to have a balanced reaction. Okay, so I have my reactants on the left and my products on the right. Okay, so the products are going to be on the right side of the equation. In addition to the atoms that are involved and how many moles of each molecule I need in order to have a balanced equation, I'm also going to have the states of matter included in my reaction. So the 3 options are G for gas, L for liquid, S for solid, and also AQ for aqueous solution. And these are going to become more important later when we start talking about, for example, binding equilibrium, because certain states of matter are not included in those types of reactions. Okay, so as I was saying before, we have 2 numbers you need to concern yourself with. We have the coefficients and the subscripts. So the coefficients are going to be inserted to balance the equation. These are the ones that you can change. You cannot change these little subscript numbers. if you change the subscript number, you change the compound. So for example, if you have CF2 and you need to balance your equation, if I were to make this instead C2F4, for example, I'm now a completely different molecule. A more obvious example of this would be with water. Right, so in this reaction where I have hydrogen and oxygen combining to form water, if I were to simply balance the equation by adding this 2 here instead of adding the 2 here and here, I've now gone from water as a product to hydrogen peroxide, which we all know has a completely different chemical physical properties and chemical properties than water does, right? So for example, hydrogen peroxide is very lethal to cells, whereas water is obviously not. Okay, so what can I find using these chemical formulas? I can calculate what's called, oh, I think I skipped a lot of steps. Give me a second. I was like, this seems really out of place. Sorry, this is my first time working with this program. Okay, so there are 3 types of reactions. Oh, no, too far. 3 types of reactions you need to concern yourself with. The first are combination reactions. You may recognize them in their generic form, where we have 2 smaller things like A plus B coming together to form a larger compound like AB. We have decomposition reactions, which are basically the opposite of this, where I have a larger compound decomposing, like think of a fungus, into its constituent atoms. So for example, A plus B. And then I have combustion reactions. So combustion, when you hear combustion, you should think burning. And this is rapid oxidation. And the hallmark of this is going to be some kind of hydrocarbon, for example, CH something, plus oxygen. And you're going to know that it's a combustion reaction because what you're going to form are carbon dioxide and water. So these are the 3 main ones that you need to know about. Okay, so here are some examples of combination reactions. So in combination reactions, we're going to have 2 or more substances combining to form one single product. So in the example here, we have, for example, magnesium and oxygen combining to form magnesium oxide. Okay, and this can happen in all different states of matter as listed on this slide. Okay, decomposition reactions, this is going to be the opposite of your combustion reaction. This is where you're going to have a larger substance, for example, calcium carbonate, that's going to break down into 2 or more substances. And there are some examples down here as well. Okay, combustion reactions generally produce a flame. So what we know about combustion reactions is that another term for it is rapid oxidation. Rapid oxidation. And basically this is burning. So in a combustion reaction, I'm going to have some kind of hydrocarbon, usually combining with oxygen as the reactant, and generally I'm going to see carbon dioxide and water as my end products. Okay, so what can I do with these chemical formulas? First of all, I can get I can calculate the formula weight of my elements. So this is going to be significant because this is what's going to allow me later to calculate or predict how much of a product I should get from any given reaction. Okay, so the formula weight, this is going to be the sum of the atomic weights for each of the chemicals in a chemical formula. And a good example here, so formula weights usually pertain, I should have said this before, to ionic compounds. So ionic compounds. If I'm talking about a covalent compound, I'm usually going to use the term molecular weight. So in this example, I have calcium chloride. So here the way that I would find the formula weight of calcium chloride is I would get the weight of, I look at how many moles of each element I have, and I multiply that stoichiometric coefficient. So in the case of calcium, that's 1. And I multiply that by the formula weight for each individual atom. So for calcium, I would look at my periodic table and I would get that that's 40.08. No, right. 08 atomic mass units, also known as grams per mole. And then I would add to that the number of moles of chlorine, so 2 moles of chlorine times the formula weight for chlorine, which is 35.453. So I would multiply these and then add the two together, giving me this answer of 110.99 atomic mass units. Again, also known as grams per mole. In contrast, a molecular weight, you find it the same way, except this is for a molecule. So this would be for a covalent compound. Covalent compound. So you do it the exact same way. So again, I'm going to use those subscripts and the stoichiometric coefficients. So in this case, I have C2H6, which means I have 2 carbons. So again, 2 times the mass of carbon, and I have 6 hydrogens, so 6 times the mass of hydrogens. I'll multiply those out, add them together, and that will give me the number of grams in 1 mole of this molecule. Okay, so just a quick reminder that ionic compounds, they have their own unique 3-dimensional order of ions, so they're just associating with each other based on the idea of opposite charges attracting. So as a result, ionic compounds use empirical formulas and formula weights, but not molecular weights. So when we are going to be saying the term molecular weight, we're always referring to covalent compounds. All right. So percent composition. In the lab we did the other day, we found out the percent composition of a given molecule. So for example, we found out what percent of our unknown mixture was ammonium chloride, what percentage of the unknown mixture was sand or silica dioxide. We found out what percentage of it was sodium chloride. So that is an accurate description of percent composition of a mixture, but you can also find out the percent composition of an actual compound. And in order to do this, you're going to rely on basically what we just calculated, either the formula weight or the molecular weight, and then basically we're answering the question, how much of a given molecule or compound is going to be attributed to a given element. So the way that we denote this is the percent composition of an element is equal to the number of atoms of that element times its atomic weight over the entire formula weight of the compound. So you can think of this, it's easier to think about it in terms of the mixture, right? So when we did the lab the other day, we found out what was the mass of, for example, the ammonium chloride, right? So we found out the mass of the ammonium chloride, and then we divided that by the total mass of the sample, and we multiplied that by 100. So it's the same idea, except now we're looking within an individual compound, how much of that compound can be attributed to carbon, how much of that compound can be attributed to sodium. All right. So let's look at ethane. So ethane is a hydrocarbon. It's got 2 carbons and 6 hydrogens, I believe. So if we wanted to find out what percentage of ethane or ethane is carbon, what I would do is I would take this number, this subscript, which tells me that I have 2 carbons. So I would do 2 times the formula weight of carbon, which I get from my periodic table. And then I'm going to divide that by, so this is my mass of carbon in my molecule. And I'm going to divide that by the total mass of my molecule. Okay, and I'll get that mass of that molecule the same way we just did before. So I would do 2 times carbon, 6 times hydrogen added together, and that gives me my total mass. So what I end up getting is 24.022, that's the mass of carbon, divided by 30.070, which is the mass of the total molecule, the total mass of 1 mole of ethane. and I multiply that by 100, and what I end up finding out is that 79.887% of ethane is actually carbon. So most of the weight. And that makes sense, right? Because carbon has an atomic mass of 12, and I have 2 of those, and even though I have 6 hydrogen, they only have a mass of around 1. So logically, it makes sense that most of the mass of ethane should be attributed to carbon. Okay, so always good to use logic to double check your answers. Okay, so in the lab, though, we don't usually work with individual molecules because they're just too small. So what we talk about is generally a mole of that thing. So when we're talking about the formula mass, we generally work in moles. And as you guys know, 1 mole, there's several definitions of it we talked about, right? 1 mole can either equal however many grams there are. That's the one that I get from the periodic table. 1 mole can equal how many things there are, right? That's the 6.022 times 10 to the 23rd things, which can be atoms, molecules, cats, ducks, chickens, doesn't matter. And then we also know that 1 mole of a gas is equal to 22.4 liters for an ideal gas. Okay, so from the periodic table, I know that 1 mole of carbon-12 has a mass of 12 grams. Okay, the molar mass is the mass of 1 mole of a substance. Again, I get this from the periodic table. If I have a molecule that's diatomic, so for example like oxygen is O2, then 1 mole of O2 would equal 2 times the mass given of oxygen on the periodic table. Okay, so how do I actually use moles? We talked about this in the beginning of the year in terms of our mole map. So I don't know if I can add a slide here. I'll just draw it down here. So we talked about using mole maps and using double mole maps. This would be a single mole map. So we have mole in the center, and then we have those 3 definitions of moles. So we have things, we have grams, and we have liters. And we have different definitions of the mole that will take us to each of those stops. So the definition that takes us from mole to things is 1 mole is equal to Avogadro's number 6.022 times 10 to the 23rd things. The definition that's going to take us from mole to grams, as we just talked about, is 1 mole is equal to the formula weight. That's what I get from the periodic table. And to get from moles to liters of an ideal gas, I use the definition 1 mole is equal to 22.4 liters. So if I'm going from moles to liters, for example, so if I have, let's say, 6 moles of CO2, and I want to know how many liters that is, I'm going to multiply it by the definition that 1 mole is 22.4 liters. So if I'm going this way, I'm going to multiply it by that conversion factor. If I'm going from liters to moles, I'm going to divide it by it. So both of these, all of these definitions can go both ways using that same definition of the mole. Okay, so this is simply saying the relationship between moles and different things. Same thing I just said on that map. Okay, so how can I use the information that's given from percent composition to calculate the empirical formula of a given compound? So first of all, we need to touch on what empirical formulas are. In the module that you were given last week, I mentioned that empirical formula is a lot like a reduced fraction. So empirical formula is the most basic ratio of the different molecules within a compound. So for example, if my molecule is C2H6, both 2 and 6 can be further simplified. So I would actually have CH3 as my empirical formula. So it's the the most reduced form of my ratios between my atoms. So we can use the percent composition to calculate the empirical formula using this little flow chart that's illustrated up here. And the way that you would do that is basically I start with the mass that I'm given, and I assume that the mass percent that I'm given, so basically those percent compositions, and I assume that I have 100 grams of my sample. And the reason why I do that is that by assuming that I have 100 grams, that allows me to easily just turn those percentages into grams. So by assuming that I have 100 grams, I can turn those mass numbers directly into the grams of each element. I can then use the molar masses to convert from grams to moles. So I'm going to use conversion with that definition that 1 mole equals how many grams, and that gives me my moles. So I started with percentage and I went through grams to get to moles. Then from those moles, I'll be able to calculate the mole ratio, and I do that by dividing by the least, or my lowest number of moles, and this will make more sense when we get to it in a second. And then from this, that will give me my mole ratio, which then tells me what my empirical formula is. So let's take a look at this. So in this example, we have para-aminobenzoic acid, also known as PABA or PABA, and this is a component of sunscreen, and it's composed of carbon, they tell us it's 61%, hydrogen 5%, nitrogen 10.21%, and 23.33% oxygen. Based on these percent compositions, they want us to find out the empirical formula of PABA. So again, what am I going to do? I'm going to use those. I'm going to go from percent to grams just by assuming 100 grams. I'm then going to go from grams to moles using my formula weights, right? Using my periodic table and those definitions of what 1 mole of each of these atoms is. And then from moles, I'm going to go from calculate my mole ratio by dividing by the smallest number of moles, and that will give me what I need to make that empirical formula. All right, so right here what they're doing is they assume they've already done the conversion from percentage into grams, so they assumed that they had 100 grams, so they just literally took those percentages and rewrote them as grams. They then took, for each element, they multiplied it by its formula weight, so I have 61 grams, 0.31 grams of carbon. I know that in 1 mole of carbon, I have 12.01 grams. Grams cancels out, and this allows me to calculate all the moles of carbon. So now I'm going to look at these different moles I have, and they're kind of all over the place, right? 5.105, 5.09, 0.7288. What I want is a simple whole number mole ratio, and in order to get that, what I need to do is divide by the least number of moles, and the element that has the lowest number of moles in this example is going to be my nitrogen. So now I'm going to take each of these mole numbers and divide them by the number of moles of nitrogen that I have in my compound, which will give me that mole ratio. So that's all I did here, is each of those numbers I divided by 0.72, giving me these rough whole numbers. So I get 7 for carbon, 7 for hydrogen, 1 for nitrogen, and 2 for oxygen. And these are the numbers that I'm going to put in my empirical formula. So from this, I simply take, so carbon has 7, so C7. Hydrogen has 7, so H7. Nitrogen has 1, so N1, the 1 is implied, and oxygen has 2, so O2. So that means my empirical formula is C7, H7, and O2. Okay, but this doesn't actually tell me how many of each atoms are actually existing in the molecule. This is that reduced fraction of the molecular formula. So if I want to convert from the empirical formula to the actual molecular formula, I need to have a little bit more information. So let's look at this problem here. Okay, so the empirical formula of a compound was found to be CH. Remember, this is that reduced fraction, so they're giving me the empirical formula. They're telling me that the compound actually has a molar mass of 78 grams per mole, and they're asking me, based on this information, what is its molecular formula? This sounds a lot worse than it is. All you need to remember is the fact that this mass must be some multiple of the mass of the empirical formula. So what I need to find is, one, what is the mass of the empirical formula? So what would be the mass of CH? And then I'm going to find out how many multiples I have between the mass that I'm given, so the actual molar mass of the compound, and the molar mass of my empirical formula. Okay, so this empirical formula, CH, if you remember, carbon has a molar mass of about 12. H has a molar mass of about 13. I'm sorry, has a mass of about 1. So 12 plus 1 is about 13 grams per mole. Okay, and 78 grams per mole is the actual molar mass of my compound. So all I need to do is take the molar mass that I'm given, which is 78, divide it by 13 to find out how many times 13 goes into 78, which the answer is right here, 6. So what that means is I have to multiply the whole molecule, this CH, or whatever my empirical formula is, by 6. So now I started with 1 and 1. So the actual true subscripts are actually C6 and H6. Okay, so there's not more examples given here. I wish I could add a blank slide to do another one. Nope. Okay. Well, I'm going to try to figure out how to do another, maybe I'll record another video of some more molecular formula examples. All right, so I'm going to end this recording here and save it and do another recording showing some more molecular formula examples, and we'll pick up here tomorrow.